At the very end of today, we're going to discuss these two words, the central angle and the intercepted arc. How many people have heard those words before? Oh, people without your hands up, you're liars. You took a geometry class. I know you learned it. Okay, but I'll tell you what it is, because we probably forgot it. So central angle and intercepted arc mean this. In a circle, okay. Oh, yeah. Good timing. Oh, yeah. Or Q, whatever. Okay, in a circle, you have a center. A central angle was an angle whose vertex was at the center of the circle. So if I draw an angle in my circle, this angle right here is my central angle, okay? Because its vertex is in the center. Then remember, if it had stretched all the way across the circle and had a vertex on the side of the circle, does anybody remember what kind of angle it was called then? Inscribed angles, right? So there are central angles, and then if it stretched all the way, it would be an inscribed angle, okay? Then a central angle or an inscribed angle, any angle inside your circle, okay, hits the circle then at certain points, and that part of the circle is an arc. We specifically call that the intercepted arc because it's like the portion of the circle that the angle intercepts. Okay, so any portion of a circle is an arc. Our angle intercepted it, so it is the intercepted arc. Okay, so it's basically like the piece of the circle that that angle engulfs as you extend it out. We're going to use that stuff later. Okay, at the very end, we're going to talk about how to find the length of that arc. Okay, so you guys in geometry, you did this. The last example we're going to do is totally, to me, like a problem I've taught in geometry before. To find the length of this arc based on knowing the angle measurement and the radius of the circle. Okay? Anybody kind of remember doing that at some point? Okay. All right. What if the arc went all the way around the circle? Okay. So then it's not an arc, it's the actual circle. What do we call the distance around the circle? Circumference. Okay. How do we calculate circumference? Okay, 2 pi r. Okay. Obviously, the radius has to be involved because if the circle gets bigger, then you're going to need more materials to go around the circle, right? The circumference is going to get larger. So that is what the radius is doing here. The way that we're using a circle, does it matter if our circle gets larger or smaller with what we're doing? So think about, remember those problems that we did and I said, oh, find this angle right here, okay? And you're like, I don't know. I can't do anything based on what it looks like. So then we put a point on here to help you. And one of the problems we saw put the point 3,3 right there. Okay? And then how big then did we determine this angle was? 45 degrees, and that was because if we drew this down, that meant this distance was 3 and this distance was 3, and we must have a 45, 45, 90 triangle, right? And that angle was 45, and if we wanted to find, say, the tangent of 45, we would do opposite over adjacent or y over x, and it would be 3 over 3, and the tangent would be 1, okay? Let's say I didn't give you the point 3,3. Let's say instead I made it longer, and I gave you the point, like, 7,7. Would that change that the angle was 45 degrees? No. Would it change the sine, the cosine, or the tangent for that angle? No. So if we're trying to find trig values of the angle, does it really matter to us how long the radius of the circle is? No. Okay? So what we tend to use is the unit circle. What do you think I'm implying about the circle by calling it the unit circle? The radius will be 1 unit. All that does for me is it takes away all the fluff. If I drew this triangle, this would be a 7, and this would be a 7. Okay? This would be a 7 rad 2. Okay? If I wanted to find the sine of this angle, I would have to do 7 over 7 rad 2. But what would happen to the 7s? Cancel out. If I did it with the 3s, I'd have 3 over 3 rad 2, and what would happen to the 3s? Cancel out. So by making it a unit circle, I get rid of all those factors that are going to cancel out, so I can just deal with the raw numbers and not have to cancel stuff out all the time. Is that okay with everybody? So if I decide to make it a unit circle to get rid of all those extra factors, that means I'm declaring that my radius okay, for my problems is going to be 1, like we said, right? Which means what is the circumference of the unit circle? 2 pi. Okay. So here's what this means. This means we used to look at the circle, and we saw this as 0 degrees all the way around to 360 degrees. It's a really ugly circle. Okay. So 0 degrees all the way around to 360 degrees. That's how we saw it. Now we're going to measure those positions in radians. Now, radians are really more measuring the position given like a certain place around the circle, a certain amount of the circumference, okay? A certain amount of like intercepted arc. So you're still going to start your initial side in the same position. So all the positioning starts the same. That's 0. You're going to go this way if they give you a positive measurement, or this way if they give you a negative measurement. But if we are now measuring in radians, one trip around the circle, if we want someone to get back to this position, we wouldn't say go 360 degrees. We would in the world of degrees. In the world of radians, how much arc would we tell them to go around? If we want them to get back to the beginning. Well, if I want to go all the way around the circle, I got to use my circumference. We said we're going to make it a unit circle because how big the circle is doesn't really matter to us in finding sine, cosine, tangent stuff. So if I want to go all the way around this unit circle, how far do I have to travel? 2 pi, the entire circumference. So this position that we used to call 360 degrees, in radians, it would be called 2 pi, but it means the same thing as 360 degrees as far as where the position is that you end up, okay? So in radian world, once around the circle is 2 pi. In degree world, it was 360 degrees. Once we knew that a circle had 360 degrees in it, what did we say to go halfway around the circle was in degrees? 180, because that was half of 360, correct? If we know that to go all the way around the circle is 2 pi radians, what is it to start at 0 and go halfway around the circle? 1 pi radians, yes. So this position, the 180 degree position, is also known as pi in radians, okay? So they're kind of taking this idea of like, hey, we don't have to give someone degrees. We know about circumference. We could tell them how much of the arc of the circle to travel around, and that's kind of what a radian is. But in the end, they're the same thing. So we're going to associate both degrees and radians as ways for someone to tell us around the circle how much to go to be in a position that we would then calculate sine or cosine or tangent of. So this is just another way for them to give us that position, okay? All right. What do you think 90 degrees is in the world of radians? Good, a half pi, or we write it as pi over 2. Okay. What about 270 degrees? Good, 3 pi over 2. Dana's got her circle down, okay? Because 270 degrees is 3 90s, right? So it's like a 90, 90, 90. Down here is 270. So in the world of pi's, it's half a pi, 1 pi. Another half of pi would make it 1.5 pi. Okay, so as a fraction, 1.5 is 3 over 2. So you normally see this written as 3 pi over 2. All right, what about at 45 degrees? So 45 degrees would normally land us in that position. If somebody wanted us to get there and wanted to give us directions in radians, what measurement would they give us in radians to represent 45 degrees? There. Good, pi over 4, because it's half of the half, right? Half of a half is a fourth, pi over 4. Okay? So that's the same thing. I'm going to write these next to it because it's going to be important to us later. That's our normally what we would call a 45-degree location. Okay? All right, what about right here at where we would normally say we were at 30 degrees? Any idea what that is in radians? Pi over 6? So how did you figure that out? Okay, good. So would you guys agree that 30 degrees is a third of 90 degrees? Okay? So if we know that 90 degrees is pi over 2, and we want a third of that, a third times a half is a sixth. So this is making this a 6. So that's where he's getting pi over 6. Okay? All right, what about at 60 degrees? What we would normally consider 60 degrees. What is that in radians? Pi over 3. How do we figure that out? Same as the other one. So you could say, well, 60 degrees is 2/3 of 90, and you can multiply 2/3 times 1/2. Or you could say, if 30 degrees is 1/6, then 60 degrees must be 2/6, and 2/6 reduces to be 1/3. And that makes sense. See, 1/6, 2/6, 90 would be 3/6, which reduces to be pi over 2. It's just a whole other world of measuring, and yes, you have to have pretty good fraction number sense about it, okay? So what tends to be the trend is this. When we first learn about radians, because we're very comfortable with degrees, we tend to do a lot of this classic unit conversion between degrees and radians, because if I ask you a question in radians, I guarantee half the people are going to convert it to degrees, then get the answer, and then if they have to, convert it back to radians or whatever the case may be. Okay? But eventually, we're going to get comfortable enough with radians to recognize some patterns and know, oh, you know what? Anything that's like a 1/6 is some sort of 30-degree thing going on, and anything that's like a 1/4 is some sort of 45-degree thing, and anything that's a 1/3 is some sort of 60-degree things, and all the halves and wholes are at the axis points. Okay? And we're just going to get used to that pattern. But is everybody okay with the general idea of now, instead of asking you the sign of negative 240, okay, I could ask you the sign of something like 5 pi over 6, and you'd be like, oh, but you'll just think about where 5 pi over 6 is and then work from there. Is that okay? So just a new way of measuring in radians. Where does it come from? It's really kind of a piece of a circumference measurement that's telling you the position on the circle rather than just telling you the central angle there to get there. Okay? Yeah, Alex? Yes. Yes. Pi would be what? Yes. And so what Alex is getting at is what we're going to use for unit conversion. So if I want to go from feet to inches, I had to know this one piece of information, at least one solid piece of information in my head that says this many inches is equal to 1 foot, so I could do the calculation, right? If I give you degrees and you want to convert it to radians, you're going to have to know one solid piece of information that says, you know what, this many radians is the same as this many degrees. So Alex just said, since 2 pi radians is the same as 360 degrees, does that mean that pi radians is the same as 180 degrees? And the answer to that is yes. Okay? And so when we do conversion between radians and degrees, I like to use this relationship, and this is what you'll see people use. It's the same thing as using 2 pi and 360, but those are both divisible by 2, and if you reduced 2 pi over 360, you would get pi over 180. Now, whether pi is in the numerator and 180 is in the denominator or the other way around depends on what you're converting to, right? Like what kind of units you want to keep and what kind of units you want to cancel out. So that's what we're going to do next. All right, so these are degree measures. We want to change them to radian measures. So notice the first one says 45 degrees. You guys already know. What should the answer be? We just did the pi over 4, okay? But in case it's something that's not one of our nice angles that we can see relationships with on the circle, let's talk about how to go through a calculation to do that. So see that degrees is the current unit, and my goal is to end up with radians. And I know you're not going to write everything out that I'm writing out each time, but for the sake of being very thorough so that we can understand it if we were confused, we want to make sure that we're canceling out degrees and being left with radians when we calculate this final answer, right? That's our goal. And then we have to have that key piece of information that this is really equal to 1, some amount of radians that's the same amount as degrees, and we're going to use what Alex pointed out, that pi radians are the same as 180 degrees, okay? And so what that means is this measurement of degrees, because of the way I've positioned them, cancels out. And so then I'm left with this fraction. We saw how we write our radians, so I'm going to go ahead and keep the pi And I'm basically going to reduce this fraction. So 45 goes into 45 one time, and 45 happens to go into 180 4 times evenly. That's how I'm getting my pi over 4 radians. Is this okay with everybody? Claire? So remember that right here, just like with feet and inches, all I'm trying to do is write something that I know is equal to convert them. And so pi and 180 is, I could do 2 pi and 360, but then I'm just going to have extra factors to cancel out. So pi and 180 is kind of the simplest form of it to use. Okay? All right, so negative 225 is up there. If we're going to convert that, we're starting with negative 225 times, again, we're canceling out degrees and ending up with radians. So pi radians is equal to 180 degrees. The degree units cancel. They leave me with units of radians. I have pi. My answer will be negative because this is a negative times a positive. It's going to come out to be negative still. And then I have to reduce the 225 and the 180. I don't know. Oh, thanks. So 45 goes in here 5 times and 45 goes in here 4 times. So negative 5 pi over 4. No? If you're just converting, you want to keep it true to the number that they had. So instead of giving, what you're doing is giving a coterminal angle to this angle. So when you're converting, you want to get the exact angle that this was. So if this was a negative value in degrees, you want to give the negative value in radians. Now if they ask for a coterminal angle to that, you could give that as a coterminal angle, another way to end up in that same spot. Okay? All right. Other thing we can do, we can convert from radians to degrees, so just make sure we can do both. I'm going to look at part A here, and then I'm going to look at part B in the U-tries, because I want you guys to see that. Notice that says 3 radians. Just because circumference is calculated with the symbol of pi in it does not mean that every radian measure will show up with pi. Around our unit circle, because we keep it as exact value, and it is based on having that circumference, we see pi. But just because you don't see pi show up in it, don't get confused, and we'll look at how that answer looks, okay? So first, for pi over 3, oh, yeah, don't know. This is yeah, I can't write. Sorry, I wrote R instead of 3. That's apparently, I don't know. Okay, so pi over 3 radians. So when I multiply by that conversion factor, I'm trying to cancel out the radians, leave me with degrees. So this means pi would be in the denominator this time with 180 in the numerator. So if you were given an angle that had pi in the numerator, you can see that those nicely cancel. 3 and 180 have a common factor of 3, so 3 goes into 3 once and into 180 60 times, and we end up with 60 degrees. If it's something like part B from the U-try where it's just 3 radians, that means pi is not going to get canceled out or go away. And you're going to have this weird answer that has like some sort of pi degrees. Oh, well, you have a weird answer that has pi in it. Pi is a number, okay? And somebody can use that number of degrees if they want to. So for part B here, if it was 3 radians, remember, again, our setup, we want to cancel out radians and leave us with degrees. So this is still 180 degrees over pi radians. So 3 times 180 is 540. I don't know. And that's how many degrees I have left. And it's really weird looking because the pi's didn't cancel out, but that is a number, and that just happens to be that number of degrees. Now, on the unit circle, most of our stuff, like you saw, is going to be pi over 6, pi over 3, pi over 4, those fractions with pi's. But I just don't want you to be confused if something like that shows up. Okay? Is this all right with everybody to convert between degrees and radians? Alex? For this one? Well, what you could do is you could divide it out. It wouldn't be exact value, though, because you'd have to round it at some point. But you could do that, depending on how they ask for the answer. Okay? All right. So now we're going to actually talk about, I don't know if you guys heard Matt's question earlier, but this is basically what he brought up, I don't know, intentionally or unintentionally. So we converted negative 225 to negative 5 pi over 4. Okay? And then he said, oh, could I name it, as like 3 pi over 4 instead, or do I have to write negative 5 pi over 4? So my answer was, if you're converting and it says negative 225, your angle in degrees should also be, or in radians, should be negative something as well, the same type of direction and way they got that angle. No extra loops, no coming from the positive side instead, exactly as it would be converted. That's a conversion, keeping it exactly the same, but just converted to the new units. What you would be doing if you picked out the positive direction to get to that angle instead of the negative one is back to that vocabulary word we talked about last time. You would be finding a coterminal angle with that. Okay? So when we wanted to find coterminal angles in degrees, what was kind of our trick? Like if I said 30 degrees, that's the angle I'm thinking of. Somebody give me an angle coterminal with 30 degrees. Min Chao. 330. Negative 330. Good. What else? 390. What are they doing to get these numbers? Adding 360 or subtracting 360, right? Okay, now let's take that same notion and move to the world of radians. Okay? So if I say pi over 2, okay? Somebody give me another way or a coterminal angle with pi over 2 but in radians. What are you going to want to do to pi over 2? Raven? Negative 3 pi over 2. What about a positive one? 2.5 pi. So where are they getting this? So he's negative 1.5 pi is what Raven comes up with. Matt says 2.5 pi. I started with half pi, basically, right? Pi over 2. Where are they coming up with these numbers in their head like that and quickly doing that? What kind of arithmetic are they doing? Bailey? Good. They're adding or subtracting 2 pi because 2 pi in the world of radians is the same as what in the world of degrees? 360. So if I was trying to find coterminal stuff in the world of degrees, and I would just add or subtract 360 because that would add or subtract different directions of loops around the circle, I want to do the same thing, but just in a different world of measurement now. So I'm just going to add or subtract 2 pi to come up with my coterminal angles in this world of radians. Does that make sense to everybody? So you're doing the same thing, just with a new type of unit of measurement. So why don't you guys go ahead and find one positive and one negative angle that are coterminal with each of these, okay? There are infinitely many answers to this. Okay, somebody give me a positive coterminal angle with 11 pi over 4. Alex. Good. So you guys see that he added 2 pi to that, and some of you might be thinking, no, adding 2 pi would be 13 pi over 4. No, that's adding 2 pi over 4. Remember that we need to make our common denominators when we're adding together fractions, okay? So if you literally write on your paper 11 pi over 4 plus 2 pi, that's a 2 pi over 1. Make a common denominator, and then you'd get here. What about a negative? Did anybody come up with another positive coterminal angle? Shannon? Good. So 3 pi over 4, and then a negative one? Good. Then notice how Shannon said when she subtracted 2 pi from this, she got 3 pi over 4. That means the two angles that you were given are coterminal angles, right? So negative 5 pi over 4 could have been a negative coterminal one for this, and 11 pi over 4 could have been a positive. Okay? All right, last thing we have to do, I think. Oh, well, we're not going to get to the arc part. We'll leave that part for you guys. Okay, so these are the same questions that were asked yesterday, but this time the angle's given in radians instead of degrees. Okay? So, tangent of negative 2 pi over 3. First, we need to position negative 2 pi over 3. So there's a couple ways to do this. You could convert negative 2 pi over 3 to degrees. Not bad. Okay? Or you can go back and look at that diagram we wrote at the beginning. Every pi over 3 represents how many degrees? 60. So if this is 2 pi over 3s, how many degrees is it? 120. We just kind of converted real quick in our head. okay, using a key piece of information that a pi over 3 was 60 degrees. So 2 pi over 3 is 120 degrees. So negative 120 degrees puts me somewhere over here, right? And remember, my reference angle is always from that terminal side back to the x-axis. If I've gone here 120 degrees, what is my reference angle? 60, because that's how much more I would need to reach 180. Okay? And then again, we could fill in the information that we'd want to fill around the 30, 60, 90, right? So shorter leg, longer leg, hypotenuse. And make sure we put the negative, so like Min Chao pointed out earlier today, what makes this different than finding sine, cosine, or tangent of 60? What makes it different and what makes it actually here at this point is that those two are negative values. Okay? All right, so we're only supposed to find the tangent. So the tangent of negative 2 pi over 3 is going to be equal to the y over the x, or the opposite over the adjacent, which in this case is negative n rad 3 over negative n, which is going to be positive rad 3. Is this okay with everybody? So I basically can turn this problem into the same problem I did in last night's homework if I understand some sort of relationship between radian measures and degree measures. Okay? Matt?
Just make sure the reference angle is not actually part of the real angle.
Right. Okay? It is when you're like up here. I mean, 60 degrees is the real angle and 60 degrees is the reference angle. Okay? So it kind of just depends on where you are. But for all the other quadrants, it's not going to be the real angle, okay? Because it's always going to be positive for a reference angle, and it's always going to just be between the terminal side and the x-axis. But what's going to make it different than this one is marking which sides are negative or positive. No. No. Because if you use the 30 degrees from here, your opposite is the x, where for us it's the y. Okay, so it would create like a new world of trigonometry where sine and cosine would mean different things than how we use them here. Okay. All right, so 3 pi over 4 for the next one, the sine of 3 pi over 4. So again, you could convert 3 pi over 4 to degrees, or if you know one of the key pieces of information we wrote in our diagram, it has a 4 in the denominator. Pi over 4 by itself is how many degrees? 45. So this is 3 of those. So how many degrees is this? 135. Okay, so it's over here. And the reference angle right here is how big? If this is 135, it's 45. All right. Okay, so my pattern there. And I only have to find the sine of 3 pi over 4. So I'm just looking at the y over r, or the opposite over hypotenuse. So n over n rad 2. So 1 over rad 2, but if you rationalize your denominators, you get root 2 over 2. Okay. All right, the only thing I want to mention is this. This is a geometry problem, but there are a couple of these in your homework. We talked about central angle and intercepted arc. This is straight out of your book that tells you exactly how to find the arc length that they ask you. Okay? You just need to do the radius, okay, times that angle. So just look at the example in the book when you get to that problem. Our focus is more on the other stuff, but it's a good geometry review to see this, okay? So homeworks 5 and